Hi, my name is Eliza Mace, and today I'll be presenting my COMS 4995 Deep Learning Final Project entitled Project Dreamhouse. Let me just share my screen really quickly. Okay, so my project is entitled Dreamhouse because it's based on housing costs and real estate. So currently the housing market is extremely active due to low interest rates. And this is inspired partly by my own browsing for homes here in Northern Virginia. But I was wondering if it's possible to predict the cost of a house just based on the way it looks from the outside or from data about the house, such as the number of bedrooms and bathrooms, and then how those things compare. And then I was also wondering if we can use GANs to generate images of housing that fit into a particular budget. So can we find someone's dream house? So the first thing I did was to create a data set. I scraped the web using the Beautiful Soup package to look for zip codes in the area I was interested in, Northern Virginia. And then I used the Redfin Houses Python package to scrape metadata about house listings from the website Redfin in the zip codes that I was interested in. Finally, I took the lat-long information in the house metadata and used the Google Street View API to get images of the houses at the various lat-long locations to go along with the housing for sale metadata. So this is a typical example from my data set. We have numerical data about the house, such as the number of bedrooms and bathrooms and the year it was built, along with the cost, which is the variable we'll be regressing on. And then finally, we have our image from Street View, which I have 600 by 600 images of each of these houses. And here's some pretty typical examples where you can see part of the view of the street, some trees, the sky, and the houses are sometimes a little bit occluded, either in this case by a tree or by the mail van. And unfortunately, this is not a perfect process, obviously. In some cases, we get much more severe occlusions, such as this case here, where the house is completely occluded by trees. I wanted to justify this to myself a little bit by saying that perhaps that actually has some predictive power, that mature trees could indicate an older neighborhood or older houses, or could be desirable for increased privacy from neighbors and cause an increase in housing prices. But in reality, I think there should be future work if there is going to be more work on this data set to mitigate the number of cases like this. One possible way to do that would be to use a pre-trained classifier on a data set such as CFAR that has trees as a class and look for examples that score high on a tree classifier, and then either take those out in an automated fashion or feed them to an annotator to either remove or keep. I did find another interesting instance in the data set. I only used images from Street View API, so I was a little confused as to how this guy showed up in my data set, but again, this is not a perfect process, so I've just assumed that there are some strange outliers in here and moved forward under that assumption. So this whole data set is available on Google Cloud Storage, and I have provided links to that in the Git repo I'll share at the end. So just to summarize, it's single family homes for sale in the Northern Virginia area in the month of October, and there are just under 2,000 images available with annotations. So then, as I mentioned, my first experiment was to see which was more predictive or able to do regression on the cost of a house, whether it was the numerical data I mentioned, so the number of bedrooms, number of bathrooms, and the year the house was built, versus the visual appearance of the house in the actual Street View images. So I'll show you, I tried a bunch of different architectures and compared the final mean squared error of the regression model. And so just as an aside here, it was important to me that these models were comparable across from the visual to the numeric. So when I did the train validation and test split for the data set, I included all of the new numerical values together alongside the image paths so that I could make sure that the same images or the same houses ended up in the train validation and test split for both the numerical model and the visual model, and that code is included in the Git repo as well. So just as a first step, I looked through the numerical data to get acquainted with the data set, used Seaborn to make some plots to see how the variables I had chosen for my numerical analysis were correlated with cost in general, and then also looked at the statistics of those numerical values. Just as a note, I noticed that my values were kind of exploding when I used the costs as written. So I divided all costs by $100,000 to kind of not normalize the variables, but make them easier for the computations to handle. And then so as a sanity check, the first thing I did was just to make a linear model in the number of bedrooms and see if I could regress on the housing cost. And as you can see here, we do see that my linear model has learned a positive trend between the number of bedrooms and the cost of the house, which makes sense because you assume that as a house gets larger and has more bedrooms, it becomes more expensive. So this was just kind of a sanity check to make sure that I was processing the data in the right way. Then I did another linear model with all 3 variables. And then finally, I did a model with a hidden layer, a dense layer, and the 3 input variables. And I just wanted to note in both of these cases, we can see that the validation loss is actually less than the training loss, which means we may be overfitting. But we'll see at the end that these models did actually perform fairly well on the held out test set. So I'll show that here. Here's the mean absolute error, over all of the training epochs, as well as the final mean absolute error, my bad, on the held out test set. So then from there, I moved on to the visual models. The first thing I tried was just a single dense layer, which did not train too well, according to the tracking of the loss. And then a little bit better was a deeper model that had 2 convolutional layers. And then finally, the last thing I trained was the pre-trained BGG16 architecture with fixed weights from pre-training, and then a single dense regression layer on top of that. So single dense layer followed by a regression layer on top of the pre-trained architecture. So as you can see in these cases, the validation loss is not less than the training loss. So that's a less indicator that we had some overfitting. So that's good. And then as you can see, this actually, I may have been overfitting because as you can see, the overall error on the training set for the deeper model, as well as the fine-tune model, was very low compared to the overall error on the validation and the held out test set. And I also thought it was interesting to note that the final performance on the fine-tune model was not actually that much better than the model that only had 2 convolutional layers. And I know we talked about in class the fact that sometimes a deeper model is not always better. And I think especially because I have such a small data set here, more and more layers aren't necessarily going to be helping. So in this case, if I was going to deploy one of these models, I would choose the model that just has 2 convolutional layers. So now on to the fun part, the GANs part. So first, I'll give a brief introduction on GANs. Generative adversarial networks. And as the name adversarial implies, we are pitting 2 forces against each other when we're doing this training process. So the first force is the generator, which is taking some random seed noise and trying to generate images that look like they're from the distribution of training images. And those images are fed as into the discriminator, which I'll describe in a second, as labeled as fake images. And the discriminator is just a regular classifier that's trained to distinguish between fake images and real images. So as I mentioned, the fake images are coming from the generator, and the real images are coming from your natural distribution that you're starting with. Then the discriminator makes a prediction on whether an image that's being presented is real or fake. And if it's able to call out or predict a fake image, that information is fed back into the generator so that the generator knows that it needs to improve the quality of images it's producing for them to be, to fool the discriminator into thinking they were from the natural distribution. So I followed TensorFlow.org's DC-GAN tutorial to get started on this project. And I made some modifications to that architecture. The biggest change I had to make was due to the image shape. The tutorial is trained on MNIST, which are much smaller images and much simpler. They don't require a larger image to get the level of detail we need. So I added more upsampling layers to get to a larger image size. And MNIST is also grayscale imagery, a single band. So I made some changes to the architecture to support RGB images. And then finally, the other modification that I made was due to the larger image size, I had to reduce the batch size because not as many images could fit in the memory of my GPU. So here are the architectures. As I described, I had to add some layers to the generator. I know that's kind of hard to read, but the fundamental unit here that we're looking at is a transpose convolution. So upsampling instead of downsampling, followed by batch normalization and a rectified linear unit layer. And then, as I mentioned, the discriminator is just a standard classifier. So this was my first attempt. I used kind of the default settings from the tutorial, and I noticed that the visual you see here is the change from epoch to epoch across the training schedule. And I noticed that the values were sort of jumping around. It wasn't necessarily smooth learning from one epoch to the next. And I hypothesized that this maybe was due to the learning rate. So I tried a different learning rate and got kind of this smoother training transition. I know these don't quite look like houses, but here I'll skip to the end. And what we can see in these images is some of the basic structures that we're looking for. We can see the ground, which is generally kind of street colored, given that we were looking at street view images. We can see the sky. We can see, green shapes that are indicative of some of that tree cover that I mentioned earlier. And we can also see some of the structure of what you might imagine in a house, horizontal and vertical lines that are common when you see, the structure of windows being stacked on top of each other, things like that. So this wasn't a perfect training process, and the data set is fairly small. So I was pretty happy with these results, with these generated images. However, this process doesn't actually fulfill the prompt that I gave earlier, which was to generate a house based on a specific budget. So to do that, what we actually need is a conditional GAN. So instead of the generator just generating an image based on some input noise and a trained model, you also are giving it a category to go alongside that, like you would in traditional classification. So I've linked the paper here about conditional GANs if you're more interested in reading more about it. But basically what you need to do is for the input layers on both your discriminator and your generator, you need to concatenate your input image with the class value that you're giving it. So what I did is I partitioned my data set into different bins based on cost ranges. And then I fed in the bin ID as a classification value to the networks. And so I followed my original implementation from the DC-GAN tutorial and modified it to take that additional input. And then I also followed this tutorial that I've linked here on getting some of that concatenation layer to work. So I can confidently say that after many training epochs, what I've decided is that everyone can save their money, because no matter what your budget is, the house for you looks exactly like this grayish blob. So this was not, the startling output that I was hoping for. But as I mentioned, this data set is very small. And I saw more success with the traditional GAN. I'm not sure that the different categories I arranged the images into were super separable. That would be an interesting experiment to do, to see, as opposed to a regression problem like we saw in the beginning, whether we could classify images based into these bins. That could perhaps lend some explanation as to why this was a hard task for the generator. So all of the code for this project is available on my GitHub that I have linked here. The information on numerical versus visual models is in the part 1 notebook. The DC-GAN is in the part 2 notebook. And then the 2 implementations of the conditional GAN are in part 2B and the example c-GAN network, with the latter being from the tutorial that I mentioned earlier. So I wanted to say thank you for a great semester and for supporting this project. Let me stop sharing my screen. And there we go. Bye.